Hey there, space enthusiasts! Get ready to blast off into the cosmos with us. Welcome to SpaceVerse, where the universe is our playground and curiosity knows no bounds. Join us on an interstellar adventure as we dive into the depths of space, uncovering its mysteries and marvels. From the secrets of black holes to the landscapes of alien worlds, we're here to ignite your imagination and expand your cosmic horizons. With mind-blowing visuals, expert insights, and the thrill of exploration, SpaceVerse is your ticket to the ultimate cosmic journey. So strap in, hit that subscribe button, and let's embark on an epic voyage together into the vast unknown of SpaceVerse. A major issue has been identified by the James Webb Space Telescope's measurements of the expansion rate of the universe. According to the findings, the Hubble tension is the most serious problem in cosmology. This indicates that the rate of cosmos expansion is exceeding our best predictions. No one knows why the cosmic model predicts. This proves our previous assumptions about the expanding cosmos to be completely wrong, and that is why it is significant. Prior to the development of next-generation observatories like the James Webb Space Telescope, astronomers speculated that the observed gap might be explained by our current technological limitations. The cosmology crisis was already bad before Webb's findings intensified it. It reveals that our estimates or observations are lacking something, which is the source of the stress. Why has the Hubble tension grown into such a major issue for astronomers, and what exactly is it? The cosmic crisis has been proven by what the James Webb Space Telescope has seen. Lastly, what new physical principles would be uncovered if the Hubble tension were resolved? Understanding the most catastrophic event in the history of the universe will need us to travel back in time to the 1920s. The astronomer Herbert Curtis and the astronomer Harlow Shapley engaged in a heated debate that is now commonly known as the Great Debate after it took place. This debate revolved primarily around the question of how large the universe actually is, whether the universe was made up of only our Milky Way galaxy or whether there were other galaxies that existed beyond it. Stretching the world beyond our wildest dreams was an issue that was both fundamental and profound. Back then, astronomers believed that the Milky Way was the only galaxy in the universe, which is something that doesn't appear to make sense anymore. For a very long time, we believed that the Andromeda Galaxy and other galaxies were star systems that were contained within the Milky Way. However, our photographs revealed that these galaxies were actually visible. Rebranding them as spiral nebulae rather than galaxies was another consequence of the same line of reasoning. Therefore, the major topic that prompted the discussion was whether or not the spiral nebulae were a part of the Milky Way region of the galaxy. The Milky Way was said to be 300,000 light-years wide, and every star system was situated on the edge of the Milky Way, said Shapley. This means that the Milky Way contained the entirety of the universe at one point. Curtis, on the other hand, maintained that the nebulae were faraway galaxies that were self-contained, similar to the Milky Way that we use. The conversation took place on Thursday, April 26, 1920. The nature of the nebulae and the extent of the cosmos were both considered to be unresolved questions at the time of the collision of ideas. The conversation, unfortunately, did not result in any significant conclusions being drawn. On the other hand, astronomers continued to disagree. Edwin Hubble, an American astronomer, was the one who did the meticulous investigation that led to the resolution of the question. It was not Shapley's or Curtis's arguments that led to the conclusion. The incredible accomplishment that Hubble accomplished in the 1920s took place at the Mount Wilson Observatory, where he had access to the most advanced telescope that was available at the time. During the time that the Andromeda Nebula was still a component of the Milky Way, he observed Cepheid variable stars within it. His attention was directed towards the Cepheid variable star B1 in the Andromeda Galaxy and the distance between it and Earth. Shapley's initial estimate of the extent of the Milky Way was almost 3 times less than the actual distance, which was around 1 million light-years. It was determined that the spiral nebulae were, in fact, enormous galaxies, which validated Curtis's initial hypothesis. In spite of the fact that Hubble's estimation was lower than the distance that we are aware of now, the universe is significantly larger than was previously believed. But this finding unleashed an outbreak. It was about to give birth to a number that would later give rise to one of the most puzzling problems in the field of cosmology. In the course of Edwin Hubble's ongoing exploration of the universe, an intriguing pattern became apparent. In his research, he discovered that galaxies that were much further away from Earth looked to be moving away from us at a faster pace as their distance from us rose. In light of this, if the velocity at which a galaxy is receding is denoted by v and the distance to the galaxy is denoted by d, then v is exactly proportional to d. The Hubble constant, which is considered to be the most controversial statistic in the field of astronomy, was derived from this seemingly basic relationship. It is imperative that you are aware of this number if you are interested in learning what the James Webb Space Telescope discovered recently. A galaxy's speed of recession from us is given by the Hubble constant, which has a straightforward physical meaning. It indicates the rate of recession in megaparsecs. It is approximately 3.26 million light-years in distance, measured in megaparsecs. Think about two galaxies. Both galaxies A and B are situated at a distance of 1 and 2 megaparsecs from the Earth, respectively. The Hubble constant indicates that galaxy A is accelerating its distance from Earth at a rate of 70 kilometers per second per megaparsec. As a result of its double distance, galaxy B would be moving backward at a speed of 140 kilometers per second. We are able to express it as 2 multiplied by 70 kilometers per second per minute, given that it is 2 miles away. This expansion is not due to galaxies physically moving through space. Rather, space is stretching as a result of this expansion. As a result, the Hubble constant is essentially a measure of the rate at which the universe is expanding. Without a doubt, you are attempting to determine what the issue is. It is possible to reduce the complexity of the problem to a straightforward linear form by determining the distance to galaxy D and its recession velocity v. Simply by entering in the values, we would be able to obtain our Hubble constant. However, if only things were that straightforward. Easy calculations can be made to determine the distance from the galaxy. With the help of a straightforward equation, determining its velocity is as simple as determining its redshift. Despite this, it has always been challenging to accurately calculate the distance. When calculating the distance to a galaxy that is millions of light-years away, what is the most accurate method that may be used? It was discovered by astronomers that there is a novel approach. Thus, a group of stars known as Cepheid variables was employed in this study. Cepheid variables are what are known as stars that have a pulsation pattern that is relatively consistent. They are capable of lighting up and going dark in a consistent manner. During her comprehensive research on these variables in the early 1900s, Henrietta Swan-Leavitt discovered a significant connection between the durations and luminosities of Cepheid variables in the Magellanic Clouds. This correlation was proven to be significantly important. The luminosity, or actual brightness, of a Cepheid star is directly related to the rate at which it experiences pulsations. Both the length of the pulsation period and the brilliance of the star are directly related to one another. The process of calculating the distance to a galaxy typically consists of 3 stages. Watching the heart rate is the first step. A Cepheid variable is now being investigated by scientists in a galaxy that is very far away. The cycles of the star's brilliance and decreasing intensity are being timed by them. As a result of the connection between the two variables, the period-luminosity relation enables us to ascertain the luminous intensity of the star under investigation. The description of this would be the absolute magnitude. Given that the entire cycle of the star takes 30 days, the absolute magnitude of the star, which is also commonly referred to as its actual brightness, would be 4.85. The second stage consists of analyzing the distinctions that exist between the two distinct forms of brightness. Through the use of telescopes, which enable us to observe the star from Earth, it is possible to determine the star's apparent brightness. For the sake of this argument, let's assume that the number is 24. As a result of the fact that the human eye has a limit of visibility of 6, the star in question is approximately 16 million times fainter than what can be seen with the naked eye. This is the third and final phase, which is the relationship between brightness and distance. A little bit of cosmic magic is required in this situation. There is a straightforward astrophysical equation known as the modulus equation that may be utilized to ascertain the distance to an object, provided that the true brightness of the object is known and that the apparent brightness of the object can be measured. Within the realm of astronomy, this is a fundamental principle. The pulsation period of the star is the first thing that we take into consideration. After that, we use the period-luminosity relation to determine the absolute brightness of the star through calculation. Using our telescopes, we will now proceed to the following phase, which is to determine the apparent brightness of the star from Earth. After completing a straightforward equation, we arrive at the conclusion that the star is located 5.9 megaparsecs away from the planet Earth. Through the utilization of a single star that belongs to a particular category, we were able to ascertain the distance to the host galaxy. Astronomers can also utilize Typeus supernovae as a substitute for Cepheids when measuring the distance to host galaxies. Both of these methods are possible. The useful size for Typeus supernovae is a few hundred megaparsecs, but the useful scale for Cepheids is tens of megaparsecs. In certain circumstances, astronomers will employ a combination of the two methods in order to validate the distance reading. Through the utilization of Cepheid variables and contemporary methods of measurement, astronomers have arrived at a figure of around 73.4 kilometers per second per megaparsec. With that being said, what is it that gives them the confidence in this figure? It was discovered that they were not. It was for this reason that they hoped to verify the figure using cosmological models for confirmation. Should the findings be consistent, then they would be correct in their assertion that the universe is expanding. On the other hand, if the numbers did not add up, it would demonstrate that our understanding of the universe is entirely incorrect. Within the context of this distinct method, the cosmic microwave background CMB, which is a leftover of the Big Bang, was employed. A faint light that is present throughout the entire universe. The cosmic microwave background CMB is the light that was there in the universe at the beginning of time. Approximately 380,000 years after the Big Bang, before galaxies and stars were produced, it depicts the universe in its original state. The cosmic distance ladder is a method that is used to evaluate the accuracy of distance measurements taken from supernovae and Cepheids. However, the measurements that are obtained by a cosmological mass spectroscopy (CMB) are not dependent on the cosmic distance ladder. Astronomers are able to track the cosmic microwave background and its minute temperature variations across the sky thanks to spacecraft such as the Plunk and the WMAP. These variations are linked to other cosmological phenomena, such as the rate at which the universe is expanding, and they are a reflection of the oscillations in density that occurred in the early past. When the astronomers utilized these two methods to determine the Hubble constant, they assumed that they would arrive at the same conclusion. Despite this, they were confronted with a peculiar turn of events. It was discovered that the CMB approach produced a value for the Hubble constant that was around 67 kilometers per second per megaparsec, lower than the value that was discovered by using Cepheids and supernovae alone. In spite of appearances, the disparity between these two figures is significant enough to justify statistical investigation. In addition, it surpasses the customary margins of error that are associated with measurements of such precision. The Hubble tension is the name given to this mismatch, which is the most important topic in the field of cosmology. One of the conflicting models of cosmic expansion is based on data in our immediate surroundings, while the other is drawn from assumptions about the early cosmos. At its core, it is a disagreement between these two models. Astronomers continue to have a positive outlook. The researchers put out the hypothesis that the gap could be attributed to the low resolution of the Hubble Space Telescope and other big observatories. For the time being, they were keeping their fingers crossed that the infrared observatory's findings from the James Webb Space Telescope would provide a solution to the problem. However, all of their most nefarious suspicions were proven correct by the evidence. Large clusters of Cepheid variable stars are frequently discovered in stellar regions when Cepheid variable stars are observed. The presence of stellar objects inside Cepheid field of vision, on the other hand, makes it more challenging to quantify brightness, which in turn has an impact on the accuracy of distance calculations. One example that stands out is a red patch in the galaxy NGC 5584 that has been identified as a Cepheid variable in photographs taken by the Wide Field Camera 3 on the Hubble Space Telescope. It would appear that this fuzzy object is surrounded by a multitude of other celestial bodies. On the other hand, the images captured by the Webb telescope display the same Cepheid variable in a more distinct manner and, more importantly, as a distant object that is distinct from surrounding stars. This is because the Webb telescope possesses stronger infrared viewing capabilities. With the findings of the scientific community, multiple Cepheid variables have been identified in two galaxies, namely NGC 4258 and NGC 5584. A nearby galaxy known as NGC 4258 is located at a distance that is known to be relatively considerable. During the same time period, the distant galaxy NGC 5584 is home to Cepheid variable stars and was the location of the Typeus supernova SN 2007 AF. Approximately 320 Cepheid variable stars from these galaxies were investigated in order to compare and contrast the capabilities of the James Webb Space Telescope and the Hubble Space Telescope. The top row displays each variable star in NGC 4258, along with its position and period, which can range anywhere from 18 to 41 days according to the star's position. Within the context of this illustration from the study, the black dots represent Hubble photographs, while the pink dots represent Webb images. In spite of the fact that the Webb photos have a substantially lower level of congestion as a result of their improved quality, the Hubble images appear to be relatively congested. Quite fittingly, the title of the research piece that discusses this subject is Crowded No More. The point of differentiation is the primary reason why this is an excellent title. In a similar vein, image patches have been shown from both telescopes for all of the Cepheids in NGC 5584 that have periods ranging from 39 to 43 days. These times are indicative of brighter Cepheid appearances. The data that were taken were used to estimate the period magnitude relation for both galaxies, which is depicted in the two panels. While the red data points are acquired from the Webb filter, the gray dots represent observations that were collected using the Hubble Space Telescope filter. We can observe that the red points follow the same pattern as the gray ones by comparing the two sets of data. However, the standard deviation has been greatly lowered for both galaxies. This is something that we can see by checking out the comparison. Among the Webb data points, it is simple to recognize a pattern. A lower standard deviation indicates a lower number of errors. As a means of providing support for their findings, the same researchers investigated 6 different galaxies in search of larger samples of Cepheid variables and supernovae. When they acquired results that supported the Hubble tension on a constant basis, they could not believe it. The researchers were able to eliminate the possibility of a measurement error being the cause of the Hubble tension as a result of this. The measurements that were carried out by the James Webb Space Telescope have established the value of the Hubble constant, which in turn has confirmed the existence of the cosmic catastrophe. Therefore, the Hubble tension is not the result of inaccuracies in measurement or limitation imposed by technical constraints. This demonstrates that our fundamental understanding of the universe is deficient, as the case may be. That is why astronomers are looking at many separate methods to determine the rate of expansion of the cosmos. One approach is to look for sources of gravitational waves, such compact objects or merging black holes. The helium flash of red giant stars may be used as an alternative distance measure, as it provides a very accurate cutoff for the intrinsic brightness of these stars. Astronomers must still ascertain the relative merits of these and other cutting-edge methods. As a result, several opportunities are opening up that could lead to a deeper comprehension of the universe as the Hubble tension increases. The most distant black hole in the universe, located on the brink of time, was just seen by the James Webb Space Telescope. A heartfelt thank you for being here with us today as we come to the end of our journey at SpaceVerse. Your support is what drives our investigation of the cosmos. Remember to hit the notification bell and subscribe to our channel so that you can continue to explore with us. See you until the next time we cross paths in the cosmos.